over some Chapter 6 stuff and some Chapter 7 stuff. The Chapter 6 stuff that I'm going to go over is collision theory, reaction rates, equilibrium, and Chatelier's principle. And I just kind of abbreviated it right there. Okay, so for collision theory, what that basically means is for a chemical reaction to happen, the molecules have to collide with each other hard enough to break their chemical bonds and then rearrange and form new bonds. So here I have A plus B. The plus sign means they're colliding with each other hard enough to break chemical bonds. And it makes chemicals C and D. And reaction rates directly relates to collision theory because, number one, if I increase the concentration of chemicals A and B, that concentration is how crowded the beaker is with chemicals A and B. If I increase the concentration, I'll increase the number of collisions per second. And if I increase the number of collisions per second, I will increase the reaction rate. Or if I increase the temperature, remember they have to collide often enough and hard enough to break the chemical bonds. If I increase the temperature, they're colliding more often, but they're also colliding harder. And if you increase the temperature, you'll have more of the molecules colliding harder to break the chemical bonds and make the products. So if I increase the temperature, I'll increase the reaction rate. Okay? Conversely, if I decrease the concentration, that means there will be fewer collisions. If there are fewer collisions per second, there will be fewer chemical reactions per second. If I decrease the temperature, there will be fewer collisions per second, and fewer of them will be hard enough to break chemical bonds. And so the reaction rate will be slower, meaning there are fewer chemical reactions every second. The other way I can speed up a chemical reaction is by the use of a catalyst. And the way a catalyst works is, and I want you to memorize this sentence, it's in the book. A catalyst provides an alternate reaction pathway that has a lower activation energy. A catalyst provides an alternate reaction pathway that has a lower activation energy. Let me give you an example of that. This is more of an analogy for you guys to get the idea. But let's say this is chemical A. We'll draw it. The chemical A is shaped like that. And chemical B is shaped like this. And let me put a little bump down here. There's a reason for it. Let me put a little bump right here. There's a reason for that. Okay? And let's pretend for this chemical reaction to happen, the nose of this has to collide inside of there just right to break the chemical bonds to make the products C and D. Well, if this is a gas phase reaction, that means chemical A and B are like Legos tumbling around in the middle of the air, and the probability when they collide that this will fit right into there with Legos is a very low probability. Okay, so that would be a slow chemical reaction. But suppose I had a metal, and there are metals that act like catalysts. For example, in your car you have what's called a catalytic converter, and it is made out of platinum. I think primarily platinum, maybe some rhodium, I'm not sure. Anyway, let's say this metal catalyst, what usually happens is they have little landing sites on them. This is an analogy. And these little landing sites are often negatively charged. And if this part of the molecule is positively charged, and that part of the molecule of B is positively charged, they will tend to be automatically attracted because opposites attract. And then I will end up with trying to draw it, guys. You can tell I'm failed out of art school. This is chemical A, and chemical B look like that. This is positively charged, this is positively charged. What the catalyst does is it attracts them and lines them up just right, so it's even easier to break the chemical bonds. They don't have to tumble around randomly in three-dimensional space and just happen to line up just right. A catalyst will attract them to the surface of the catalyst with these little landing sites that lines them up just right. That attracting them to a surface and lining them up just right is what we mean by alternate reaction pathway. In this example, the original reaction pathway is these guys are randomly tumbling in three-dimensional space, and boy, I hope they line up just right to break chemical bonds. Alternatively, if I have a catalyst, they'll be attracted to the surface of the catalyst's landing sites, and that will automatically tend to line them up so that they line up and break in just the right angle. That's an alternate reaction pathway with a lower activation energy. So if I were to draw for this guy the reaction coordinate diagram, where this is A and B, this is C and D, and let me make this hill bigger. This is the activation energy. The catalyst, because it has this alternate, better, more optimized reaction pathway, has a lower EA catalyst, has a lower activation energy because it lines them up just right, so all of them are lined up just right to break the chemical bonds. Okay? And if you have a lower activation energy, the reaction will be even faster. By the way, when I look at this, is this chemical reaction endothermic or exothermic? Well, I'm starting, this is reaction progress. This is energy. If I'm starting at high energy and ending up at low energy, it is exothermic. I've given off energy. And just as a reminder, this difference right here is the heat of the reaction, or called enthalpy of reaction, if we do the chemical reaction at constant pressure. So there, I've done collision theory, reaction rate, next is equilibrium, and then Le Chatelier's principle. So, some chemical reactions go only one way. A plus B makes C and D. If you take a piece of paper and you burn it, paper and a little bit of and oxygen, right? It's burning. It'll produce carbon dioxide, some water, and some ash, which is carbon solid in the form of soot. And you never see carbon dioxide and water and carbon soot automatically go backwards and make paper, right? That is an irreversible reaction. Irreversible means it only goes one way and that's it, no going backwards. However, some reactions are reversible. Some reactions are reversible. And that is when chemical A and B collide with each other in the forward reaction. I'll put an F for forward to make chemical C and D. But once A and B make enough chemical C and D products, these can collide with each other, break their chemical bonds, and reform chemicals A and B. Let's call that the reverse reaction. Okay? And they're reversible. Where there's a special state that says when the forward reaction rate, again, reaction rate is how many chemical reactions per second. When the forward reaction rate is equal to the reverse reaction rate, that's the number of chemical reactions going backwards every second. When the forward reaction rate is equal to the reverse reaction rate, this is said to be in equilibrium. This is a dynamic equilibrium, in that it's not equilibrium in the sense that the reactions stop and nothing change. It's equilibrium in the sense of the rate of going forward is equal to the rate of going backwards. It's kind of like if you went to the airport and they have those moving sidewalks. You know how little kids always like to get on the moving sidewalk going the wrong way? If they get on the moving sidewalk going the wrong way and they walk forward at the same pace that the moving sidewalk is going backwards, they will stay in place. That would be an example of dynamic equilibrium, what we're talking about here. That's different than if I'm just standing on a normal sidewalk and I'm not moving at all. That is static equilibrium. That's not what we're talking about here. This is like the little kid, the forward reaction is like the little kid walking forward. And the reverse reaction is like the sidewalk, automatic sidewalk going backwards at the same rate. So nothing moves, but nothing moves because there's a lot going on in opposite directions. Okay, so it's important to know. Well, it's called equilibrium, like I said. And let me rewrite this. Here I'm going to put my balancing coefficients, right? Those, the little a and the little b and the little c and the little d would be the 2 and the 3 and the 1 and the 2 that's needed to balance the chemical equation. And we have these little double half arrows like that. That implies chemical equilibrium. When it's in chemical equilibrium, or equilibrium, right, we can write this thing called the I can't write today, equilibrium constant, and it is defined as K equals products the moles per liter, or the concentration of the products, divided by the concentration of the reactants. And don't forget, This side is always the product side, and this side is always the reactants side. Now, I'll get to how to write this and then we'll solve a couple of them. But if K is bigger than 1, that means at equilibrium you have a lot more products than you do reactants. Okay, so like for example, if K was equal to 10, that's really 10 over 1, right? So if my equilibrium constant was equal to 10, that means I have 10 times more products than I do reactants. 10 over 1, it's a ratio of 10 to 1. So if K is bigger than 1 at equilibrium, that means at equilibrium I have mostly products. If K was less than 1, that means products is smaller than reactants. That means I have mostly reactants and not much in the way of products. For example, if K was 0.1, 0.1 is really 1 over 10 in my example here. So if K is less than 1, that means the reactants is a lot more than the products at equilibrium. It's not always 10 to 1. Those are just examples that I gave, but you guys get the idea. Okay? So let's learn how to write the equilibrium constant expression. And the way it's defined by chemists is concentration of the products, chemical C to the C power, chemical D to the D coefficient power, over chemical A to the A power, chemical B to the little b power. And that's how it would be written if I wanted to, when I write the equilibrium constant expression. Okay? Equilibrium constant can refer to just the letter K or this whole concept, or it could refer to the number. What's the value of the equilibrium constant? Oh, it is 1.8 times 10 to the minus 5. This is usually called the equilibrium constant expression. It's the equation for the equilibrium constant. So let's say I have here, let's say, just make it up an equation. H2 gas plus O2 gas, no, not O2 gas, I want to use N2 gas, is in equilibrium with NH3 gas. First thing I notice is that this equation is in equilibrium, but the way they wrote it is unbalanced. They didn't write the recipe right. So to balance this, I have 2 nitrogens here. I need to put a 2 right there. That gives me 2 nitrogens, because remember, this means NH3 plus NH3 if I put a 2 in the front. So I got 2 nitrogens. But then how many hydrogens do I have? 3 plus 3 is 6, or 2 times 3 is 6. So if I put a 3 here, that gives me a total of 6 hydrogens. Because that means H2 plus H2 plus H2 plus N2 will give me NH3 plus NH3. That's basically what it means, but nobody wants to write all that stuff because it's a lot of stuff. If I were to write the equilibrium constant expression for this, I would write K equals products over reactants, NH3, what's the coefficient in front? It's a 2, so it'd be squared. And let's say here I have H2, products over reactants, H2. What's the coefficient in front? It's a 3, so it needs to be cubed. And I have N2, and remember now, it's multiply, not add. I have N2. What's the coefficient in front? An invisible understood 1, so I just leave my invisible understood 1 right there. That's how you write an equilibrium constant expression. Let's say at equilibrium, So I take some hydrogen, some nitrogen, I put it in a container right here with a lid. I put some hydrogen in there and some nitrogen in there, and they wait a long time. And then I find ammonia floating around in there. And then I measure the amounts of each one at equilibrium. And let's say the H2 concentration is 0.50 moles of hydrogen per liter. And at equilibrium, the concentration of this is 0.35 moles per liter. And at equilibrium, again, I sample inside here, and I measure the concentration. I get, let's say, 0.45 moles per liter. And these are all the equilibrium concentrations. I wait a long time until the forward reaction rate and the reverse reaction rate end up being equal. Let's say I want to calculate the value of the equilibrium constant now and interpret it. I would write K equals NH3 squared over H2 cubed times N2 to the invisible understood 1 power. That'll be 0.45 squared. When we do equilibrium constants, we ignore the units. I mentioned earlier that I would explain why. Just take my word for it for now. Okay? When we do equilibrium constant expressions, the units all magically cancel out because of this thing called activity. But you don't need to know that. Hydrogen concentration at equilibrium was 0.50, and I have to put cubed, and this is 0.35, and then I want to calculate this. So I'm going to go 0.45 squared divided by 0.35 divided by 0.5 cubed, and I get here 4.6, if I did it right. Let me check one more time. 0.45 squared divided by 0.5 cubed divided by 0.35. Yeah, I got 4.6. 2 sig figs, 2 sig figs, 2 sig figs, 2 sig figs. Is this value of K larger than 1? Yes, it is. Since it's larger than 1, that means in that container that I had, where I had H2 and N2, and then ammonia appeared because it's being formed, NH3, in this container, this number means if I sample in here, I'm going to find a lot more of this than I will of the H2 and the N2. So we would say the equilibrium lies on the product side. Okay? That's what that means. All right? Now, that's how they calculate and interpret the equilibrium constant. Let's do Le Chatelier's principle. And for those of you that speak French, you know I'm pronouncing it horribly. I apologize. Le Chatelier's principle says that any stress placed on a system at equilibrium will shift to reduce that stress. It'll shift to either the product side or shift to the reactant side. Shift means I will make more products, or shift to the reactant side means I will make more reactants. Okay? So, first thing we want to look at for Le Chatelier's principle is the volume of the container. I've got my H2 and my N2 and my NH3. I'm not putting the numbers here. We see this here. Okay? If I squish, and this is, let's say this represents the volume of the container. Right? Let's do it like this. All right, that'll give me the volume of the length of the container, but pretend we're calculating the volume. If I squish the volume into a smaller space, it's going to shift to whichever side gives the least moles of reaction, least moles of product. I misspoke. If I reduce it into a smaller volume, it's going to shift to whichever side gives me the fewest moles of gas. Here in this reaction, I have this side. I have 4 moles. I got to look at the gas. I have 4 moles of gas on this side. Over here, I have 2 moles of gas. If I squish this into a smaller volume, it's going to shift to the product side, meaning I'll end up making more moles of ammonia gas, more products, if I shift it into squish it into a smaller volume. Okay? So if I reduce the volume, it'll shift to whichever side has the least moles of gas. Least moles of gas. If I increase the volume, I pull that piston up, I make the container bigger. That's all I do. I don't put more chemicals in there. I just make the container bigger. Instead of shifting to the side with the least moles of gas, it'll shift to the side with the most moles of gas in order to fill up the container. So if I increase the volume, this side has 4 moles of gas. Gotta look at the G's. 4 moles of gas here, 2 moles of gas here. If I increase the volume, it'll shift over here to your left-hand side, the reactant side, to make more moles of gas, because I need more moles of gas to fill up the container. All right? So, don't think necessarily if I squish it, it goes to the product or anything like that. Just if I squish it into a smaller volume, it'll shift to the side with the least moles of gas. If I increase the volume, it'll shift to whichever side has the most moles of gas. Okay? Now, what if instead of changing the volume of my container, I change the concentration of something? Let's say I pump into the container more nitrogen. Won't more nitrogen mean you got more nitrogens colliding into the hydrogens? It will. So if you put in more nitrogen, it speeds up the forward reaction, meaning the equilibrium will shift from reactants towards the products to alleviate or remove the extra nitrogen you put in there. If I were to add more hydrogen, I would have more collisions here. And if I add more product, here gas, again, it'll shift. Excuse me, I misspoke. If I have more reactant, I added more hydrogen, I will have more collisions among the reactants. And that means the forward reaction will go and I will make more products. So we would say if I added more hydrogen or I added more nitrogen, the equilibrium will shift to the product side. What do you guys think would happen if I pumped in there more ammonia? Well, if I add more ammonia, I'm increasing this concentration. If I increase this concentration, I speed up the reverse reaction. So if I increase this concentration, the equilibrium will shift to the reactant side, and I will have more products, more reactants than I had before. I keep misspeaking. I apologize for that. So if I add more products, it'll shift to the other side, to the reactant side. If you take away something, it shifts to the side that you took stuff away. If I were to take away some nitrogen, I would slow down the forward reaction rate, and the equilibrium would shift this way to make more nitrogen to make up for what was lost. So if you add a chemical and it's a reactant, it'll go to the other side. If you add a chemical and it's a product, it'll go to the other side. But if you take away a chemical, it'll shift to the same side of the reaction of the chemicals that were taken away. So if I take away some hydrogen or nitrogen, the forward reaction rate is temporarily slowed down. And that means the ammonia can make more of this, and it will, and we would say the reaction shifted to the reactant side. Got it right that time. If I were to take away ammonia from the container, that means the reverse reaction rate would be slowed down, and the forward reaction rate would overwhelm the reverse reaction rate and would make more product. So again, if you add a chemical, whether it's reactant or product, if you add a chemical, it will shift or go to the other side. If you take away a chemical, it'll shift to the side of the stuff you took away. Okay? You have to practice that. Right? That's Le Chatelier's principle in a nutshell. I don't think the book went over Le Chatelier's principle with endothermic and exothermic reactions. I'll have to double check that. If it did, I will come back to that and recover it and go over it again. It's a little bit harder, but I'll go over that again. Okay? What I want to go over now are intermolecular forces. Those are forces between